Thanks for the introduction. Before I forget it, this is obviously a joint work with a lot of other people who have contributed to what I'm going to present over the time, including members of our team, Hermann Herdig, our head of the group, and administrators at two HPC computing centers in Dresden and in Jülich. So I'm from an operating systems group, so you can expect some operating system stuff. And in HPC, there are a number of ways to build an operating system. And one of the traditional ways is to use a dedicated and specialized kernel, which is nowadays often called a lightweight kernel, that gives applications just what they need. That comes usually with good performance and low noise, but compatibility and features are quite often a problem. One example of this architecture could be the compute node kernel running on Blue Gene systems. Now, developers often want more, especially in terms of compatibility and features, and that's why a lot of systems nowadays run on Linux. And they are often tweaked in order to have lower noise and try to combine all these advantages. Unfortunately, it's also a fast-moving target, so these systems typically have rather old versions of the Linux kernel that often also do not change. And now there are Cray and Argo are examples for this, and many other system vendors use this approach too. And there are a number of projects that try to combine the both approaches. That means you set aside a small number of cores where you run Linux, and a lightweight kernel is then responsible for the applications that run on the majority of the cores. And that gives you no noise because of the lightweight kernel properties, good compatibility because you have Linux. And the way this works is that if there's any system call that the lightweight kernel doesn't support, this is forwarded to Linux. This usually requires some form of proxy, and that's depending on how you implement it and what you want to accelerate. That's more or less work. But it's quite a number of effort. And there are several projects like MOS from Intel that's currently doing this, MCKernel at Riken in Japan, and the Hobbs Kitten project where also Ron is a part of. So we are also in the middle area, and we are building a system that is similar to that. And now this is Mac, and of course I want to talk about how to use MPI on top of such a system. And actually MPI was a driver for the architecture of our system. So I will start with version 1 of how to get MPI on top of our system. That actually started out as a student project. So what do we have? So we also have a lightweight kernel, which is the L4 microkernel. That's been developed in our group for 20 years now. That can also act as a hypervisor, but I'm going to talk about that later. Now, this microkernel usually doesn't do anything. It's sort of like a CPU driver, and device drivers, protocol stacks, and file systems you typically put into user space servers on top of that. I'm not going to talk about them, but assume that they are there, and then there's a C library on top of that. And this allows us to take more or less ordinary POSIX compliant programs and port them to our system. So this is, for example, what the student did with the MPI library, MPICH in this case, and some applications. So we rewrote the build system and made it compile for our architecture. And in this initial version, we also had the MPI process manager running on the same node for technical reasons. Now, MPI already supports shared memory communication on the same node, and we could just reuse this using the Nemesis shared memory backend of MPICH, for example. So that required a few adaptations in order to get access to the shared memory. The APIs are sometimes a bit different, but that was not a big problem. Unfortunately, there's also PMI, the process manager interface, and that required a bit more engineering because we don't actually have a TCP socket abstraction. at least not one that we wanted to use in this project. So we created an adaptation layer that mimics the semantics of a socket interface on top of some shared memory infrastructure. So this was the initial port, and we ported also a few benchmarks and test programs. And since this is mostly shared memory and accessing the CPU directly, you would expect not much performance variability. So the details here are not important. This is some ping pong benchmark, but basically Linux and L4 are performing more or less the same. Actually, we have a few hiccups in Linux here. I don't know where they come from. But that's to be expected. This is not always the case. Here we have a difference between Linux, which is at the top, and L4, which is slightly below in terms of performance. That's because our system uses an embedded C library, which doesn't have very efficient, well, at least not for HPC, very efficient memory allocation routines. But in principle, it worked. This is actually the output of the first MPI program that I ported to this. So we had a number of these. So basically what we can say is it did work. So we had benchmarks and test programs. We also had larger applications, or at least more well-known ones, like HPL, for example. And we also ported CP2K, which is actually a quite large package. So if you include all the dependencies, that's like 1 million lines of code in Fortran, C++, and C. And once we had all the dependencies compiled for our platform, which required rewriting the makefiles and so on, we started that, and it was actually quite amazing to see that it worked. So I was really surprised that it did something with water molecules. I don't remember exactly. So it worked. Performance is, as I said, more or less what you would expect, but there's a major limitation because there was no network backend. This is also why we had the MPI process manager running on the same node. But this was a student project. So version 1 of to get MPI on top of our platform is what we actually thought would be what we wanted to have. And this is some hybrid architecture. To explain how this works, I would like to make a small detour. So what we experienced is that quite often in complex software systems, you have some operations or some subsystems that are critical to the goal that you want to achieve, but they also usually tend to be relatively small. And then you have a large, complex part that is more or less uncritical. That applies in a number of scenarios, like, for example, real-time or security and resilience. And let me give one example. For example, in security, because I have a background there. If you have cryptographic secrets and you want to protect them, so the critical part of the software is typically all the crypto algorithms and the shielding of the code that and the memory that is dealing with these keys. But everything else you don't really care about and can also have security holes. So in this regard, this is uncritical. And quite often, this also means that an entire commodity operating system can be uncritical. It's still necessary because it provides a lot of stuff, but for your specific goal, this is not really important, at least for achieving the goal. And now we thought we might try to apply the same principle of splitting software into critical and uncritical parts to HPC. And the critical part here, of course, is the performance. And for that, the MPI application and the library is obviously the critical part that we want to have running directly on the microkernel because it, for example, provides low noise. Also, communication drivers sort of fall into the category of this is critical, and but not entirely. Part of this is actually in Linux. So this is the general architecture that we thought we could try. So let me talk about a few details with regard to the InfiniBand driver. So what we see here is the kernel part of a standard InfiniBand driver, like, for example, for Mellanox cards. You have the driver inside the kernel. You have some generic IB verbs infrastructure, and there's an interface exposed to user space through character devices that you can open and do I/O controls and so on. And then there's also I/O memory, which the hardware itself exposes, and the driver is accessing these I/O registers in order to perform certain operations. But with these drivers, there's actually a second part, which is the user space part of the driver that is running in user space inside the address space of an application together with libIB verbs. So this part talks to the kernel through these device nodes, but it also has a certain subset of the memory mapped I/O registers mapped directly into the user space. So it can directly program the card for certain types of operations, like, for example, sending and receiving data, RDMA read and write operations, and things like event polling. So this is sort of the fast path for accessing the hardware. The slow path is going through these file descriptors and perform operations such as setting up connections and registering memory buffers, and also blocking inside the kernel. And it's pretty clear what's performance critical, and that part we wanted to have on Linux. So we ported the IB verbs library and the user space part of the Mellanox driver to our L4 microkernel. So we have this application running now, and this application is running there, and we also map the device registers that usually the Linux process would see in its address space into the address space of the L4 process. So we also get direct access, and everything is fast. Of course, there's still the other part of the interface that need to be accommodated for. So for that, we require some kind of proxy process that is running on top of Linux. And there's one for each MPI process that is running on L4, or InfiniBand process on L4. This is not only needed for forwarding requests to these device files, but also for registering memory buffers. And one thing that is important there is that you actually need very fine-grained control about where in memory these, or in virtual memory, these buffers end up, or at least the proxy needs to track what the offset is to the real location. So that's the job of this proxy. So with this, actually everything worked. So we had MPICH now, so we upgraded to MPICH because we needed InfiniBand support, running on top of L4, and Linux was also running there and providing these proxy services I was talking about. Now, this worked, but it was also quite hard to maintain. And that's because there's not just InfiniBand that we need to forward, but there's also BSD sockets because the process manager is running on a different node, and people want to have parallel file systems. We do have file systems on L4, but not ones that store petabytes of data. So we need proxies for that as well. We don't have a proxy for each process and each subsystem. They are co-located, but still there are a lot of them. And eventually they quite literally fell apart because some communication infrastructure was changed. So we figured out that this is probably not the right approach. It worked, but it's very hard to maintain. So for version 2, we thought, well, if turning L4 into something that Linux-like programs, like MPI programs, like, if that's too difficult, why not try to start from the Linux side? So we have MPI programs running as unmodified Linux programs on top of a Linux kernel, one that we call L4 Linux, because it is actually running directly on the L4 microkernel. And the special thing about this is that the microkernel controls all the resources in the system, all the cores, for example, all the memory and so on. And also gives us lightweight and easy modifiability and low noise if we need it. Now, a special thing about the way that L4 Linux works is that it's not using hardware-assisted virtualization, but it is very tightly coupled with the L4 microkernel. So That essentially even means that it's not programming hardware page tables directly, but it's using microkernel APIs in order to do that. And that eventually results in each Linux user process being actually executed in an L4 address space. So the microkernel knows about address spaces, and it also knows about threads that exist in there. And that also means that whenever there's a system call that a Linux program wants to make in order to call the L4 Linux kernel, the microkernel knows about this because there's an exception that is being forwarded. Now this is boring. It just means that it works. But what we can do with this is we can do something that we call decoupling. And decoupling means that we take a Linux thread that is executing code inside this Linux address space in this user process and move it to a dedicated L4 thread that is running and is under control of the microkernel and executing on its own dedicated core. Okay, so like this. And that's possible because the microkernel knows what address spaces are and it can control on which CPUs they become visible. Now, what happens if such a program does not compute but wants to do a system call? Well, then an exception is generated and the thread migrates back into Linux. The original thread context is updated with new execution state. The system call is executed, and after that is completed, we can continue running. So we get basically a noise-free environment where we can do computations without worrying about anything that is going on in Linux. Also, this allows us to perform L4 system calls if we want to. But I'm going to talk about that later. So we can do things like use the scheduling threads and memory APIs. And also what's important is that we still have direct access to I/O memory for the device drivers. So this scheme I showed before with the FASTPATH where the user space driver can directly access the hardware MMIO registers, that still works. Okay, so we did a few benchmarks of this platform and we compared it with Linux. So what we see here is we have some execution time of the benchmark. This is embarrassingly parallel, running on a number of nodes. And each of the numbers here represents the size of the configuration. So 30 cores, 90 cores, up to 750 cores. And what this line shows is the minimum execution time that any of the MPI ranks on any of the cores showed during the experiment with Linux. This is the maximum execution time. And you see this is different from the minimum one. So there's some variance in execution time taking place, and this is precisely the OS noise. When we use our decoupling mechanism, we get a slightly improved minimal execution time, and this is the maximum execution time. So unfortunately, this is not a flat line like we would have on the Blue Gene system, but there are still a few increases in runtime. We are not entirely sure what this is. This is not software. We are pretty sure about that. We actually observed that the clock rate on some of the cores went down, so probably they were overheating. So this might be hardware noise. Okay, and this was also temporarily because all the cores involved in this experiment, they are also used in these, and there they are fast. So when you have a tightly coupled application, like a BSP-style application, where you have communication compute cycles, that of course means that any delay anywhere causes the whole application to slow down, not just an individual core. And this is what happens with when you run ordinary Linux, and this is when you enable decoupling, then you get better performance. Now, if you closely observe the y-axis, this is just 1%. But if the number of cores increases dramatically, also these delays tend to increase. There are models that show that. And also, actually, the Linux distribution that we used here is quite benevolent because there's not really much going on. Actually, we have data from a vendor-provided Linux where we have execution time jitter in this benchmark or in a similar benchmark that is about 10% instead of 1%. So that's might be much more in reality. Okay, so actually what we now did is we did not use our microkernel really because it's sitting idle and not causing any noise. But I already mentioned that you can also use L4 system calls for certain operations where that might be interesting. And one thing that we think might be interesting is handling of interrupts. So why is this important? First, I have to say this is work in progress. In the context of MPI and so on and InfiniBand, this is not completed yet, but I can at least explain what this is supposed to provide. So this is the problem. We've seen pictures like these before. Okay, we have some application. This is some weather code that was fed with a very unfortunate piece of input data where we have small clouds and lots of open sky in between, and so this resulted in imbalanced computation demands. And what you can see is that all the red areas in this diagram, these are actually times where individual processes wait in MPI in order to send or receive. So this is wasted time basically. And typically we have busy waiting in order to wait when the message is there. Now the problem is you can do two things with that. Let me go back. You can try to save energy during all the waiting phases, or you can try to use the time to compute something else. And one way to compute something else is to oversubscribe. Gene talked about this, that this might make sense. I think Ron also agrees that it might make sense. And adaptive MPI from the Charm++ people also does precisely that. So this diagram, let me briefly explain it. So we have the number of MPI processes per node, and this is the total number of nodes. And we kept the problem size the same and just increased the number of MPI processes in order to oversubscribe. So, and there's a total of 4 cores in this small system per node. So this is the execution time of our benchmark with ordinary setup, 1 MPI rank per core. And when you oversubscribe, you actually get this. Instead of getting faster, it gets way slower. And that's because the scheduler of the OS cannot determine whether the program is busy waiting and could do something else, or whether it's doing useful computation. For this, so busy waiting is bad. For this particular application, it actually does not matter if you block inside the kernel instead of polling, at least not much. So on a larger configuration with 112 nodes, we tried also the same program with a similar workload, but a bit bigger, and this time with blocking, and there we actually see an improvement. So the best performance we get with 2 times oversubscription, of course. And that's actually with 0 effort on behalf of the application developer, pretty close to what the load balancer inside the application would do. But we disabled this during these experiments in order to see how this works. Now, all these experiments, they were done on ordinary Linux. So standard Linux is responsible for blocking on incoming messages that arrive over InfiniBand. But we think we can do better. And to explain why, let me briefly show you let's call it a cartoon of what happens when an interrupt comes. Okay, so in a standard software stack with Linux, an interrupt comes in, it's delivered to some routine inside the Linux kernel, and then some stuff goes on with a few indirections, and there's even a scheduling decision involved. And at some point, a user level thread might be woken up. What we actually want is to do something like this. So bypass Linux more or less completely and deliver the interrupt directly to a user space thread running in our application. So that's the goal. In principle, this works. So, animation bug, I'm sorry. So these are measurements for a very simple benchmark where we determine the latency of delivering an interrupt or an external event that occurred to a user space thread. And on the left-hand side, we see the latencies that we measured for Linux. So on the y-axis, the number of occurrences for all the events. So if there's no load on the system, we can barely see in this diagram on purpose that most of the times are close to the y-axis. So a relatively short latency, but in extreme cases it can be more than 300 microseconds. That's with Linux. Now, it first looks like this is worse with L4, but in fact, L4 is 2 orders of magnitude better in terms of latency for interrupt delivery to a user space task. And this is with our decoupling stuff that I explained a few slides before. And we think that might actually, yes?
So without load, are they basically the same, similar?
It's the same benchmark?
No, so is the performance or the latency very similar when there is no load?
And there's, I don't know.
In the without load scenario?
Yeah.
In the blue line, are they basically very similar?
Oh, no, they are not similar. So we are about 0.6 microseconds here, and here we are, I think it's 2 microseconds. Yeah, sorry, I forgot to point that out.
What does with load represent? So what sort of load is the...
So that's actually load that is also stressing the kernel. So this is from a real-time paper, this data. So it might be that this is an extreme case, but this is what can happen. Okay, so if we had MPI ranks that are doing lots of system calls for a brief period of time, registering memory buffers or whatever, something like this could happen. We also know that there's a lower bound in terms of event delivery to user space. So with a different version, with a different implementation of the L4 microkernel idea, called L4 Nova, we actually measured interrupt delivery times from the kernel handler to user space of 0.3 microseconds. So that's about 900 cycles. And it's on the same hardware as for the experiments above. So some fairly recent Intel CPU. So that's why we think if we could do this, for example, with interrupts that arrive from the InfiniBand host channel adapter, we might actually reduce the costs of using blocking in an MPI or any InfiniBand-based application. But I have to say that this is not completed yet. Yeah, we are still working on it, so I can't give any numbers. But this is stuff that we measured in some related scenario. Okay, so let me conclude the talk. So we have this L4 microkernel, which we thought would be a reasonably good lightweight kernel for HPC applications. We combine it with L4 Linux in order to get the compatibility that we require. And we have this decoupling mechanism which allows us basically to combine the benefits of both worlds. What probably was not clear from my presentation is that this system is binary compatible with regard to the applications. There's a fairly simple to use sysfs interface which controls this decoupling mechanism. And actually, in the current implementation, there's no modification to MPICH whatsoever. This used to be different in the past, where we at least had to rewrite the build system, and also certain tweaking was necessary in order to make it compile directly as an L4 application. But right now, there are no modifications. We think that if this InfiniBand interrupt unblocking stuff finally works, there's an opportunity to actually make a few changes in MPICH that's related to shared memory, but that needs to be checked. So the lessons learned. Yeah, you should try to maximize reuse and minimize the critical path. That's sort of obvious, but it was confirmed that this applies to HPC too. What was a bit surprising, and which is also the reason why we sort of went off in the wrong direction first, is that for HPC, where you require a lot of functionality because of these applications, it's probably a better idea to start from Linux and try to remove everything that is in the way of getting good performance or low latency, and not try to make L4 a better Linux. So that's why we have version 1 and 2, basically. Okay, so this is the funding sources, and there's source code available, which hopefully at some point also includes the decoupling patches, and there's the project website, and with that I'm done.